So we have finally made it to an area of a little bit of familiarity, at least, because the determinant is an operation that we use pretty heavily in Calculus 3 to do various things. So hopefully this video will feel a little bit more comfortable and a little bit more at home, but we'll finally be able to understand some of the reasons for using the determinant and some different results that it gives. So the determinant has a whole bunch of uses and a whole bunch of meanings, but the idea is that, you know, from Calculus 3, we may remember that if I've given you a matrix such as like 1, 2, 3, 4, and we're talking about calculating the determinant of this matrix, so then the determinant of this 2 by 2 matrix A is denoted, it's denoted DET A, or determinant of A. It's denoted determinant of A, and also by the absolute value of A. That's what those the bars are. These vertical bars, and is calculated. It's calculated. So for a general matrix, which is probably a better thing to have here, a general 2 by 2 matrix here. So it's going to be AD minus BC. So in the example of the matrix here that I've given you, this should not come as any surprise, but the determinant of the matrix 1, 2, 3, 4 is going to be 1 times 4 minus 2 times 3, which is 4 minus 6, which is negative 2. And that's what we get. So, you know, this process of doing the determinant is actually not too bad. It can be a little bit tedious at times, but doing it is not hard. And so we can extend the idea to larger matrices. So, for example, if we have some generic 3 by 3 matrix, A, B, C, D, E, F, G, H, I. So extending this a little bit generally, now that we have a little bit of experience under our belt. So in the past, the way that you've done this in Calculus 3 is you circle this first thing and then you cross out the first row and first column, and you say the answer is going to be A times the determinant of E, F, H, I, and then there's a subtract symbol here, and you do the same thing again for B. You go 1 over and you do this, and you say, okay, it's a B times the determinant of D, F, G, I, and then you do, for the last one, it's going to be back to a plus, and you do C, and you cross these out, and you're looking at those values, and so what's left over here is going to be that little box. So we're going to have C times the determinant, I'm running out of space, C times the determinant of C, E, G, and H. Okay, great. So this is how we did it back in Calculus 3 without really too much rhyme or reason. But I'm going to introduce to you the general idea of how to do this and a little bit more of a formality to it. So this is just to like kickstart, like, okay, I've worked with a determinant before. I should know how to do it for a 2 by 2. I should know how to do it for a 3 by 3. What else do we need to know? That's kind of what this video is about. So let's move on to the part that, the rest that we need to know. All right, here we go. So more formally, so the determinant of a matrix A is only defined, it's only a thing that you can calculate for n by n matrices. Okay, they have to be square matrices. Generally, like speaking very generally, the formula formula for calculating the determinant. Formula for calculating the determinant is the following. So you get it by doing a sum, because we're adding up a bunch of things. So we do a finite sum of j is equal to 1 all the way to n. I'm going to write down some stuff here and try and explain each part. So here's -1 to the 1 plus j times a sub 1j times this determinant of a sub 1j. Okay, so let's try and take a look at what this thing really means. So let's suppose that we have some really big matrix that we're trying to take the determinant of. And a big matrix has components, you know, row 1, column 1, row 1, column 2, dot, 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 row 1, column n, and then row 2, column 1, dot, 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 row 2, or excuse me, row 1, or row n, sorry, column 1, and then so on and so forth, a sub n. Okay, so it has all of these pieces here, and they all kind of fill out exactly where they need to. So what is this sigma notation, right? Well, sigma notation is a shorthand way of writing, you know, a whole bunch of things that we're adding together. And you may notice that what this means is if we kind of look at what's going on here, right? So if j is equal to 1, right, what's going on here? So clearly we're counting from the first row to the nth row that we have, or the first column to the nth column that we have. But what this is basically doing is it's saying, look, in order to get your first term, right, if j is 1, then what do we get? This first term here, that's just a positive 1, so it's nothing. We get a sub 1, 1 times the determinant of this remaining matrix a sub 1, 1. And this determinant bit here, that's something that I haven't defined yet. This chunk right here basically says that when you put the circle around this to get your a1, 1, and you go through the business of crossing out these terms, this a1, 1 matrix is everything else that's here, and that's what we're calculating the determinant of, which is exactly what we did in the 3x3 example up here when we were running through this and coming up with the little formula. Oops, erased too much. So when we were coming up with this little formula up here, we would circle the a term, cross these out, and we would say, okay, the first term is a multiplied by the determinant of kind of what's left over, and I just inserted it here. Well, for larger matrices, we can kind of generalize this process as this is what happens. Okay, and then when you run through the, when you head to the second term, so what happens when j is equal to 2? Well, now we have a negative that shows up, right? We get a minus 1 times something. Then we're going to be moving on to the a sub 1 comma 2 term, which is, again, across this first row. And so we're going to get a sub 1, 2, and then times the determinant of the a sub 1, 2, kind of the remaining matrix that we get when we, that's not right, when we cross out this. So it's going to be the matrix that we get from this stuff and this stuff over here, and so on and so forth. Okay, so this is like a very shorthand notation of how do you approach it for larger matrices. In general, there's actually a trick for remembering this. So it turns out, if you kind of follow the pattern, if you put like if I zoom in here, I can put a plus sign on the first one, a minus sign on the first one, a plus sign on the third one, dot, 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 and I could do a minus sign here and a plus sign here and a minus sign here and dot, 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 and it creates this alternating sort of pattern. And that's how you can remember that the first term here, right, if we're expanding along this first term in the first row, first column, that this one here is positive. When we get to the next term, the next one is negative, and so on and so forth. This naturally brings up the question, why do I have them on all of these? Because it turns out that you can expand the determinants. You can basically calculate the determinant by expanding along any row or any column that you want. So I'm going to write that down because it's very important. So, star. Okay. we can calculate the determinant of some matrix A by expanding along any row or column that we choose. Okay, we just have to keep track of the signs. Okay, so we just have to keep track of the signs. That's really the only thing that we need to focus on. So if you're doing one of these problems and you have a really big matrix you're trying to calculate the determinant of, I would write down plus, minus, plus, minus, 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 plus, minus, plus, right? I would fill this out with all the things. That way, you can decide then which one you want to expand upon and make sure that your signs end up in the correct place. Okay, so for example, maybe to just kind of give an example here, if I give you the matrix, so let's do a 3 by 3, but let's do one where I do like 2, 0, 0, 3, negative 4, 1, 6, 2, 9. Okay, if I do this the original way, okay, so first off, the first thing that I would do, so if I'm asked to calculate the determinant of A, okay, the first thing that I would do is I would put a plus, I'd put a minus, I'd put a plus, I'd put a minus, I'd put a plus, and a minus, and a plus, and a minus, and a plus, like so. And those don't affect the numbers in this matrix, but they do affect where, how I'm going to calculate my determinant. So if I choose that I want to expand along this first row here, then I do this the same way. So, using our little formula or using any, practical methods that you may have remembered from before, the first term here, so determinant of A is going to be 2 times the determinant of this remaining matrix here. So we're going to get 3, 2, negative 4, 9. Okay, and again, you might be wondering, Dylan, I thought you put pluses and minuses here. Don't I need to have like a minus here and a plus sign here? No. Those pink things that I put there are just to act as a guide for figuring out whether or not the coefficient is going to be positive or negative. That's it. So then at this point, since we're going to move on to the second piece, which is going to be this negative 1, we're going to take that, and so it's a minus 1 because of that pink thing, even though the term itself is actually a positive 1. Okay, the original matrix I gave you is a positive 1. We get that minus sign. We do our expansion, so times the determinant of 0, positive 2, 0, positive 9. And then our last piece that we're going to get, I'll erase this because it's kind of in the way a little bit. Okay, and then the last piece that we're going to get is plus. The pink plus is letting me know that I'm going to have a plus 6 times the determinant of whatever's left over here. So in this case, 0, 3, 0, negative 4. So let's calculate this really quick. So if we do this, we're going to get, all right, this first thing, all right, so the determinant, we're going to get 3 times 9 is 27 minus a negative 8. What's 27 plus 8? 35. So 35 times 2 is 70, so that's going to be 70 minus, here we get 0 minus 0, so minus 0, and then here we get 0 minus 0, so that's also 0. So this is going to equal 70. Fantastic. Now this is all fine and dandy. We chose to expand along the first row, no problem. But I could also have chosen to do this problem by expanding along the first column. Now, why would that be a good choice? Well, this is a good choice because we have a bunch of zeros in this column. So for instance, if I want to do this same process, right, I'm going to use the pink pluses and minuses to, guide me again. So determinant of A, again, is going to equal, we're going to use this and do just like we normally do, scratch that out. So we're going to get 2 times the determinant of 3, 2, negative 4, and 9. But now what's going to happen? Well, it turns out that because we're going to get minus, but then this next term here in this column is 0 times the determinant of whatever the heck else we get. But last time I checked, 0 times anything is 0. So we move on to the third one. And, moving on to the third one, we get plus 0 times, again, another determinant, but I don't care what that determinant is because we're just going to get 0 again here. So really, we actually only need to calculate this first determinant, which we already did in the last problem. We know that was 70. So it turns out, in this particular problem, this is super slick. It's really, really nice and a very easy way to go about evaluating this determinant. So that's a nice trick. If you ever see a matrix and you're asked to evaluate a determinant, it's a good idea to pick a row or a column that has a bunch of zeros in it, or maybe some easier numbers that you would like to work with. Okay, so now that we have, the idea is we can calculate the determinant, we can calculate the determinant along any row and any column. That's not a problem at all. And so now, we noticed that in this particular matrix, we had a lot of zeros. And this is actually a good time for me to introduce a particular type of matrix to you all. So I'm going to bring up this new matrix definition. Maybe it's just a classification, but what we call a triangular matrix. A triangular matrix is any matrix that consists of zeros above or below the main diagonal of the matrix. And of course, we're talking about, these are for n by n matrices, square matrices, n by n matrices, okay? So as an example, 2, 0, 3, 4 is a triangular matrix because this is what we call the main diagonal of the matrix. This is the main diagonal. And we have a bunch of zeros below it, aka just 1 in this case. Another example would be if I gave 2, 3, 4, and then 5, 6, 7, and then I had 0, 0, 0 here. This is a triangular matrix as well because, again, here is the main diagonal of this matrix, and we have a whole bunch of zeros above it. So, these have like other classifications. The first one is technically called an upper triangular matrix, and this one is called a lower triangular matrix. Why do you think they're called triangular matrices? Because they kind of form little triangles when you look at them. So that's pretty much it. And why am I bringing these up? Because it turns out that the more zeros you have, the easier it is to calculate your determinant. So much so that there's a nice little theorem for it. So theorem, if you have a triangular matrix, A, then the determinant of A is just equal to the product of the diagonal entries. Okay, the diagonal entries. All right. Now, why is this going to make sense? Well, let's see if I can show it using the example that I just gave right above. If we try and do this, it's probably a good idea to expand along this row right here. And if I expand along that row, because everything else is going to become 0, the determinant of the matrix 2, 0, 0, 5, 3, 0, 6, 7, 4, if I'm expanding along that first row and the last two terms are going to be 0, the only one that I'm going to have to really concern myself with is going to be this 2, which is positive because it's going to be the first one, so it's a positive 2, times the determinant of what's left over, 3, ooh, I should go inside the thing, 3, 0, 7, 4. And then this thing itself, you'll notice that if I calculate the determinant of what I just came up with, the determinant of this is just going to be the diagonals 3 times 4 minus 0 because this piece gets eviscerated because there's a 0 there. And you'll also notice that this itself is a triangular matrix, and it follows the pattern that the determinant of this ends up being 3 times 4, again, because when you multiply by the other diagonal, the off diagonal you will, you're going to get just a 0 there. And so it turns out that the solution here is just 2 times 3 times 4, which is what we would have gotten if we had multiplied these diagonals in the first place. So that's a really slick trick. If you notice that your matrix is a diagonal matrix, you can just bust this trick out and use it really quickly. Okay, so why did I bother to bring this up? Because there's more theory. Okay, so here's another theorem. So theorem. All right. So let's let A be a square matrix. So be an n by n matrix. All right. So then, number one, if a multiple of one row of A, is added to produce a new matrix B, then the determinant of A is still equal to the determinant of B. So basically, if we do one of our standard operations, so if you add rows together or you multiply a row times a number and add it to another one, we still get the same determinant. Determinant of A is equal to determinant of B. The second thing here is if you swap rows, then you get that the determinant of B is equal to the negative determinant of A. So that's if you do one row swap. So if you do 2 row swaps, you get back to the positive version, okay? And then for the last one, step 3, if one row of A is multiplied, by K to produce B, then the determinant of B is going to be equal to K times the determinant of A. So why am I telling you all of this? The reason why I'm telling you all of this is because what this basically said is that I can manipulate a given matrix, something like the one that I've given you before, or something much worse. And what we can do with it is we could RREF it into something that is much, much easier to look at, or get it to the point where it looks like a triangular matrix, at the very least in just regular echelon form, and then we can calculate the determinant with no hesitation. We're not going to have anything to worry about. So, for example, calculate the determinants of, let's do just the matrix 1, 2, 3, 4. Okay, we already know how to do this, right? We did this earlier. It equals -2. But what I want to do right now is I'm going to take the matrix itself. I'm going to take 1, 2, 3, 4. And what I'm going to do is I'm going to do some row operations to it. I'm going to try and get it into echelon form. So what that's going to look like for me here is I'm going to replace row 2, and I'm going to take -3 times row 1, and what am I going to do with that? I'm going to add it to row 2 to get a new row 2. So what does that give me? That gives me the matrix 1, 2, 0, and then we're going to have, up here, we're going to have -6 plus 4 is going to give me a -2. And now, all we've done, now at this point, we can say, oh, dang, right? This was our starting matrix A. I did some operation to give me a B. We look at our set of rules, and the only thing that we did is we did a row operation, right? We multiplied a row by something, we added it to something else, we got a new matrix B. And so for this, that means the determinant of the first matrix A should equal the determinant of the second matrix. And because this is a triangular matrix, we can just, this is an upper triangular matrix. Since this is an upper triangular matrix, we can just multiply the diagonals together, and sure enough, we get -2. Now, one thing that kind of drives people up the wall is sometimes they say, hey, I don't get the difference between numbers 1 and 3. Aren't we multiplying both of them by something? Why, I multiplied by -3 here. How come that's not showing up in the determinant? It would show up if I took this matrix and I multiplied it arbitrarily. Like let's say I took it and created a new matrix that had a, let's just say I multiply it by -3 on the top, so -6, 0, and -2, and I didn't do anything with it, right? So if I left it in this form, along the way, or here, maybe I'll write it over here. Remember that, kind of as an intermediary step here, you're multiplying row 1 by -3, and then you add it to row 2, and so you'd have -3, -6, 0, and -2. But clearly, at this point, if you decide to take something like this and calculate the determinant, you wouldn't get -2. We would get that the determinant would be +6. And we're going to be off by the factor of -3 because I multiplied this first row by -3 and I never undid that. So that kind of carried through to my determinant answer, and it sets it off. So you could leave it in this form. You can definitely do that. The only thing is, when you get this answer, you need to keep track of the fact that, oh yeah, I multiplied row 1 by -3, and I never undid that. So that means this determinant, I need to divide by -3 to get me -2, to get me the actual answer. Whereas in this version up here, we have this step inherently said that we multiplied the first row by -3 and then we redivided it by -3 because we didn't actually change the first row, right? We multiplied it by -3, did something, then divided by -3, we were good to go. All we essentially did after that was just do some row addition. And row addition, which is what's kind of listed up here, row addition does not change the determinant. Okie dokie. So these are just, this is a cool rule, and so this is a good technique if you're dealing with really large matrices like a 5 by 5 or a 6 by 6, and you're asked to calculate the determinant. It's a lot nicer to calculate it by doing a little bit of row reduction and getting it to be in echelon form, and then just multiplying the diagonals and just making sure that you've kept track of all your operations and you haven't left any multiples or anything like that lying around. Okay. So before I get to the punchline of all this, which is like, why do we care about determinants and what do they really do? I would like to just bring up some notation that the textbook has. It's good notation to know. So if you remember that little formula that we had earlier for calculating the determinant of a matrix, it can kind of be expanded upon in the following way. Oops, I is equal to 1. J is equal to 1 to n, and we have -1 to the I plus j times a sub I sub j times the determinant of our a sub I sub j. So this, now that we have a little bit of exposure under our belt, is the same thing as we did before, but this right here incorporates the fact that we can calculate the determinant by expanding on any row or column. Okay, that's essentially what this means. So there are two summations here now, which basically just means that we would scan all of the rows, all of the columns of our matrix, and the idea is that if you are on the first row or the first column or whatever, whichever you decide to do, you're going to run through the same process. And you'll notice that this kind of follows our plus minus pattern, right? If we're on the first row and the first column, first row, first column, these are going to add up to be 2. That's going to give us a positive. We're going to get a plus here. If we're on the first row in the second column, this is going to give us a 3, so we're going to get a -1, and that's going to make this a negative sign. Oops, that's going to be a negative sign in the second one, and so on and so forth. So this helps basically give us just that alternating pattern. But one thing that I wanted to point out is that in the textbook, they call the -1 to the I plus j bit times the determinant a sub ij. They call this thing the cofactor of a, essentially. The cofactor of a at ij, and it's denoted c sub ij. And so one thing you might read in the textbook at some point is that they might ask you, oh, calculate the determinant using cofactor expansion. And cofactor expansion is a really fancy way of basically that when you calculate the determinant of a matrix A, you're doing, if you're going across, say, a particular row, then it's like A sub, going across any particular, this is going to be a column if I do this one, but A sub 1, A sub I sub 1, and then the first cofactor plus A sub I2 in the second cofactor, this is a column because we're moving columns, plus dot 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 plus A sub in, C sub in. This is all they mean with cofactor expansion. So this is basically you have a matrix, you have your little A sub 1 1, your A sub 1 2, your dot 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 A sub 1 n, your A sub 1 n, and it's basically like, look, if you pick the ith row to expand upon, then you're going to go like this, and you're going to go like this, and you're going to keep going and add all those up, and all of these, the cofactor business is just, it's basically just the determinant of everything that's left over, but it also, comes with the whether or not it's plus or minus. So this is just another shorthand way of writing the same thing. It's on page 198 of the textbook. If you're interested in looking at the notation yourself, it's written there in all of its glory. I don't really use the word cofactor expansion too much. I'm just like, you pick your row or you pick your column, and then you multiply by the determinant of everything else, and you remember the plus or minus sign by the little pattern we came up with. But the cofactor expansion and calling it a cofactor and stuff works just dandy. Okay, so that out of the way, it's just something small that I kind of have to talk to you about. But now we're at the much more interesting question, which is why do we care about the determinant? Right? Why do we care about the determinant of A? And let me tell you, this is going to be your freaking best friend. So let me give you a matrix. I'm going to see if you can come up with the reason why yourself. Let me give you a matrix A. And let's say that this matrix, I'm going to just make one up, as I always do, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm going to give you this. Let's pretend, now that doesn't actually do this, but let's pretend that I were to do some row operations, and I were to get to the point where this thing reduced to, 7, -1, 0, 0, 4, 2, 0, 0, 0. Okay? What if I get here? The first thing is, right, what is the determinant then of this matrix? Well, immediately we see a row of zeros, which means I can expand and figure out the determinant by expanding upon that row of zeros. And that means immediately that the determinant of this matrix is going to equal 0. Okay? And you're like, well, Dylan, you mentioned all these rules, what if you swapped rows to get here, and what if you multiplied by something? Wouldn't that affect the answer? Sure, but this answer by expanding along this particular row of zeros is going to give us 0. So no matter what operations you did to get there, if at some point you get a row of zeros, your determinant is just going to be 0 because nothing you multiply by it is going to change the fact that it's 0. Okay, why is this a big deal? This is a huge deal because what can you tell me about the columns of this matrix if when you row reduce them, you get a row of zeros. What does that immediately tell us? It immediately tells us this matrix implies that the columns of A, the column vectors of A, are what? They are linearly dependent. They're literally dependent. And what did we learn from the last video on inverses? If they're linearly dependent, then we cannot, if A is a transformation, then we cannot span, this would not span all of R3, right? If we were to talk about the span of the columns of A, this would not span all of R3, and that in and of itself implies a whole bunch of stuff. This implies that then A is not invertible. Okay, A is not invertible. There's no inverse. We can't come up with it. That in and of itself gives us things like our matrix might not be, or the transformation might not be 1-to-1. It's definitely not onto, because if it was onto, it would cover all of R3. So this is a very, very, very quick shortcut to figuring out whether or not the columns of your matrix are linearly dependent or independent, and whether or not an inverse of this matrix exists. So theorem, okay, if, or I'll say it even better, the columns of an n by n matrix A are linearly independent if and only if the determinant of that matrix is not equal to 0. If the determinant of A is equal to 0, that means at some point we were able to row reduce this thing down and get a row of zeros somewhere along the way. And because of that, we get linear dependence. Okay, that's going to give us a 0 determinant. It's going to give us linear dependence immediately. So that is this is in terms of the theory, the largest thing you should take away from this video right here. And you need to watch this a couple times to make sure that you feel comfortable with connecting these topics right here. And that I would suggest to go back to the last video on the invertible matrix theorem, because this is another extra tidbit that we get from that theorem. This is something we can tack onto it. So the very last thing for this exceedingly long video is going to be, there is also a geometric interpretation of what the determinant is, right? Because we know that the determinant now, you're all right, so there's some theory, right? We can calculate the determinant through this bizarre process of adding a bunch of cofactors, or AKA adding a bunch of smaller determinants, and we get a number at the end, and that's cool and all, and there's some theory behind it. We basically just showed that if you calculate the determinant of A as 0, we get some information of it, great. But what does this actually mean? Okay, sure, it has implications if we're viewing A as a transformation, but what does this mean? And specifically because in Calculus 3, we learned that the determinant can give you things like the area of parallelograms and stuff like that. So I'm going to talk about that really quick. And the only one I'm going to talk about is for a 2x2 determinant. Okay, so this is in the textbook as well as in 3.3, and I believe it's part of your homework and you should read it. But from Calc 3, okay, why does the determinant of two vectors give you the area of the parallelogram generated by those two vectors? Parallelogram generated by those two vectors. Why does that happen? Okay, this is a big thing that we use all the time in Calc 4 for sure, but we learn about it a bit in Calculus 3. So the question is, why does this happen? The best way for me to do this is to, let's just say, let's do a V example. Okay, so V example. Let's pretend, I'll draw us a little picture that we have two vectors. Okay, and for the sake of just simplicity, okay, I'm going to say that we have one vector here, and this is going to be the vector 5, 0. And I'm going to have another vector, say, over here. This is going to be, I don't know, should I do something that's not so crazy? Let's do 10, 3. Okay. And I claim that if I sketch out the parallelogram that's generated by these two vectors, that, then the determinant of the matrix that we get by taking 10, 3, and 5, 0 as the columns is going to give us the area of that parallelogram. Parallelogram. Okay. And so here's the idea, the reason why it works. Okay, this is of course via an example, and a much more rigorous proof is presented in the textbook in 3.3, but I think it's good to just kind of provide a little bit of intuition. So the idea here is that first and foremost, you have to remember that the area of a parallelogram is given by just the base times the height, right? Like times the height of this parallelogram. Right? It's base times height. Well, last time I checked, this is the base, right? That's the base, which has length 5. And this is the height, which has length 3. And so we would expect that the determinant here would be 15, right? And of course, when we look over here, what's going to happen? Well, you're going to say, uh-oh, you're going to get 0 minus 15. You're going to get, oh no, the answer is negative 15. If we're talking about area, then we're going to obviously be considering the absolute value of the determinant. Okay, so when you're talking about area, you're talking about volume and practical applications, then we're talking about using the absolute values. If you feel weird about that, just swap the order of which you put these into the matrix. Remember that if you swap like a row, it changes the sign of the determinant from positive to negative. The same thing if you swap a column. So here now all of a sudden our answer is positive 15. Okay, but if you think about like, oh Dylan, you just arbitrarily swapped that. No, I didn't. I was just like, look, you put in one vector, you put in another vector, you calculate the determinant, you get an answer. So when we're talking practical applications, put an absolute value, we want positive answers. But anywho, like I said, we expect to get 5, 3, great. Okay, we can kind of see that it works here by punching these two in. And so the idea is like, okay, well, how do you show that this, like why does this work? Right? Why does this give us an area of 15? What you can do, it turns out, because all we need is the height of essentially this parallelogram, it turns out that what I can do is I can take this orange vector here, and what I'm going to do is I'm going to add some multiple of that blue vector to it. And you're like, what do I mean? I'm going to add -2 of this blue vector, -2 of this blue vector here. And what is that going to give me? That is going to give me exactly what we're looking for. This is going to give me a new shape whose bottom vector here is still 5, 0. But now this part here is going to be a new vector 0, 3. And you're like, all right, great, right? Because like that, that just gives me this new vector right here, 0, 3. You're like, how does that help us? Well, because this little new square that I just built, this little square right here, that guy right there has to have the same area as this parallelogram because they both have the same height and they both have the same width. And you're like, okay, those have to be true. And if those have to be true, if you're okay with the fact that what I just said is true, that the area of a parallelogram is base times height, the area of a square is base times height, the area of a rectangle is base times height, then this vector right here is just the vector 0, 3. That it was like this 10 didn't even matter in the first place. And so calculating the area of this thing would be the same thing as calculating the determinant of these two vectors, right? I could pop in 5, 0, I could pop in 0, 3, and I would still get the same answer. I'm still going to get positive 15. And we don't even need to do this. This is just a kind of a redundancy check, because what we're more interested in is that the area of this rectangle, just using good old-fashioned arithmetic, was 15, and it matches what we did here. This is just to help you with some like concrete numbers so that you kind of believe like, okay, like there's some actual algebraic understanding of this. If you're interested in the like concrete theory, go to 3.3. Let me pull it up. 3.3, it is on page, it starts on page 215 and goes to page 216, and they kind of prove it a little bit more generally. But that's the idea. The idea is that I could take, no matter how funky my vectors are, if I took a vector up here and I took another vector over here, that I could like grab them. I could rotate them so that they're flat, and then I could adjust them, and it turns out that all of these operations end up making it so that the determinant of these two vectors gives you the area of the parallelogram generated by those two vectors. And so the same thing kind of holds when you talk about the determinant of a 3 by 3 matrix that has 3 rows, of course, and 3 columns. But the difference is now that since we have we have a vector going this way, a vector going this way, but now we have one going up as well, what we get is we get actually like this what's called a paralleloiped. We basically get like a rectangular prism of sorts, or like a parallelogram-esque rectangular prism, and the determinant of those three 3 by 3 matrix, that 3 by 3 matrix, which consists of a bunch of 3D vectors, for example 1, 2, 3, 4, 5, 6, 7, 8, 9. If you want to try and interpret some geometric meaning from this, this would give you the volume of this parallelepiped. Okay, that is generated, that is outlined by these 3 column vectors right here. Okay, so it kind of makes a jump from 2D to 3D. And again, the proofs are on page 215 and 216. And of course, you're welcome to email me, and we can meet up to chat about it, or chat about it in office hours if you'd like. Okay, so this was a pretty jam-packed video, a lot of stuff. We went through the basics of like calculating a determinant all the way to what I would consider as the most important stuff. The most important part of this video was right here with determinants, and talking about like what a zero determinant really tells you about your matrix, and what a non-zero determinant tells you about your matrix. And then of course there's like some geometric interpretation if you feel like you need something to kind of hold on to. It kind of also makes sense that if your vectors are linearly dependent, you would get, right, what happens if your vectors are linearly dependent? You get a determinant of 0, because if these vectors are going in the same way, right, if this vector and the other one is going the same way, what's going to be the area of the parallelogram? Well, there isn't going to be a parallelogram, right, because the vectors that you have are stacked on top of each other, so you would get an area of 0, which should kind of make sense as well. Okay, so this was a really long video. I'm going to stop talking now and let you guys get to it. That's going to do it for this week. And whenever you're ready, hop in the homework, and then we'll, get started with the next stuff.